All right, the triangle midsegment theorem. First, some vocab. The midsegment of a triangle is a segment that connects the midpoints of two sides of a triangle. So, for instance, if I'm going to just estimate the midpoints. If I have that midpoint there, actually, let's label this triangle first. A, B, C, because we're creative like that, and we'll label some midpoints. That midpoint there we'll call D, we'll call this one E, and we'll call this one, yeah, let's make that look a little closer. Okay, F. Okay, I just estimated where the midpoints were. Okay, now based on that, what I know based on those markings is that if that's the midpoint, then AD is congruent to BD, right? I would know that AF is congruent to CF, and I would know that BE is congruent to CE. Okay, and so if I connect those midpoints, I get what's called a midsegment triangle. All right, when all three midsegments are connected to form a triangle, you get a midsegment triangle. All right, and so I've got my midsegment triangle right here. There's some things we'll learn about that midsegment triangle and those midsegments here in future slides, but that's some vocab for us. Okay? All right, so using the midsegments in a coordinate plane. So I've got you this triangle here. In this triangle ABC, we want to show that DE, the midsegment, is parallel to AC, and that DE is 1/2 of AC. I guess I should have pointed out that DE is a midsegment, but you can kind of calculate that, right? I mean, if I look at this and I say, well, to get from A to B, I have to rise 2, and I have to run, oops, that's kind of weird. Anyway, I rise 2, and I run 8. So really, if I were to rise 1 and run 4, that would be the midsegment, and that's what happened, or the midpoint. And so kind of the same thing this way. If I look at C and I go to B, I'm going over 4. So I'm running 4 and I'm rising. Looks like 8. Okay, which means if I go over 2 and go up 4, yep, there's my midsegment at E, or midpoint at E. So we want to show that DE is parallel to AC. So how could we do that? Well, we know that parallel lines have the same slope. So let's look at slope. There's a couple ways to do this. If you're given a picture, finding slope's a lot easier. So let me get rid of all this other stuff that I've drawn on here. You don't have to on yours if you sketched yours out, but finding slope's easy if you have a picture. You're just looking at rise and run. So if I look at the slope, oops, excuse me there. Come on now. The slope of AC. All right. And we go, well, to go from C, or from A, we have to go, A to C, we have to go down a grand total of 6, and we go over a grand total of, looks like 1, 2, 3, and 4. So the slope, our rise is -6, our run is 4, so our slope is -3 over 2. So just remember you're dealing with rise and run. Okay, we got a slope of -3 over 2. All right, now if you're like, whoa, I'm not even given a picture, I really don't want to graph it, I'm just giving points. Well, then remember you can always use, and I'm not going to do this right now, but you could always use the slope formula. Slope formula is y2 minus y1 over x2 minus x1. So you could use the slope formula if you had to. I don't know why I put in parentheses there. You know, if you looked at point A and you said, well, I'm at -3, 2, and point C, you're at 1, -4. You could think of this as x1, y1, and not y, x2, y2. Okay. I'm not going to calculate that out, but it will give you -3/2. The slope of DE is the next thing we need. Okay, so remember M means slope, and I'm just putting in subscript DE. So I'm going to look at D. It looks like I go down 3 and over 2, 3 and over 2. Okay, so notice we have the same slope of -3/2. Therefore, AC is parallel to DE. All right, so we've got slope we've dealt with. Now we also need to show this piece here. Okay, actually, let's use a different color for that. Okay, where it shows DE is 1/2 of AC. And so really what we're looking for there is distance. Okay, so you could use the distance formula. Distance formula is equal to, remember, the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Okay, and so if you've used the slope formula, you already have x2 minus x1. It's right here. And y2 minus y1, it's right here. You just plug those numbers in and you square them. And really, we know those numbers. They're -3 and 2, right? I mean, that's a big jump if you're not familiar with what I'm talking about. So I'm not going to kind of go that route, but it's really helpful if you've done it that way. Okay. What I'm going to go ahead and do is I'm going to go ahead and look at, you know what? Actually, better yet, just to show the slope formula real quick, I am going to calculate it out using one of those. Okay, so let's do that here. So y2 minus y1 and x2 minus x1. All right, and let me erase these. And we will label them over here since we're doing DE. This will kind of maybe help draw some connections here for another area. So we got 1, 3 and 0, 3. And we'll call this one x1, y1 and x2, y2. And it really doesn't matter which one's which, remember. But so I've got 3 minus 3. No, this was not 3. You know what? I flipped these around. Let's fix that real quick. Those of you are like, what is he doing? Whoops, I almost did it again. Okay. That should be 3, 0. Okay, so we have 3 minus 0. Over 1 minus 3. Okay, and that gives us +3 over -2, which is the same as -3 over +2. They're both -3/2. Doesn't matter where you put the negative. We are good to go. Okay, so now if I were to calculate the distance of DE, I'm trying to prove that DE is half of AC. Well, if I find the distance of DE, not M, but distance, and we'll say of DE, okay, well, again, that's x2 minus x1 quantity squared plus y2 minus y1 quantity squared. So note, that means that this and this are the same thing, and we know that that was 3. So really, when I'm looking at the square root, back here I have a 3 in there, and it's being squared. Now you can actually plug in the points, but that's what you get. You already plugged in the points up here. And let's switch the color of the highlighter here. This is that, which is that, and no, x2 minus x1 is that. So that means right here we have -2, and we're squaring that. Okay, and so let me grab that color again. We'll highlight this. So really, that's kind of a quick route. I know it took me a little longer, but if you're using points, that's kind of a nice route to go. And calculating that, you get 4, negative times negative is positive, plus 9, which is root 13. Okay. The other route you can go, and I'll show it using AC. If you have a picture, it's a little faster. You've already calculated a triangle. There's a right triangle right here, right? Okay. You know the lengths of those triangles. So this is like a squared plus b squared equals c squared. Well, rather than calling it c squared, let's call it d squared. Right? Okay, so if we go a squared and b squared and d squared, well, a squared is 36 and b squared is 16, or 4 squared. So d squared would have to be, well, 36 and 16 is 52, the square root of 52. So that means, oops, sorry, it's 52. So d is the square root of 52. Okay, or you're like, what in the world is he talking about? Well, you could just say a squared plus b squared, not d squared, plus b squared equals c squared. You can use that right triangle, which would give you 6 squared plus 4 squared is equal to c squared. Okay, I know we called that d, so maybe we should call it d squared there. Okay, so that gives me 36 plus 16 is equal to d squared, and 52 equals d squared, which means d is equal to the root of 50. Oops. Whoa. All right, let's fix that up. Okay, root of 52. And looking at that, you're like, hold on, that does not look like, I'm trying to figure that out. If DE is supposed to be half of AC, right? That's the math behind it. Really, that means DE, which is root 13. So if we kind of plug in what we know, root 13, that's what DE is, right? Is equal to 1/2 of, well, AC is root 52. How in the world? Yeah, that doesn't, I mean, you can use your calculator. Well, root 52 simplifies, right? So let's actually simplify root 52 here. Root 52 is the same thing as root 4 by root 13. And root 4 is 2. So that is 2 root 13. So root 52 is not just root 52, it's also 2 root 13. And 2 root 13, 1/2 of 2, those cancel, right? Half of 2 is 1. That means root 13 is on the right and root 13 is on the left. That means DE is equal to 1/2 AC. You've just shown it right there. Okay? All right. Okay. Then it says find the missing endpoints of the missing endpoint of the other two segments, mid segments. So I'm going to have to erase a little work over here to show where that is. But the missing endpoint, remember, if I go down 6 and over 4 to find a midpoint, I could go down 3 and over 2, half of that. And that gives me my missing endpoint there. So if we were to call that point F, that is my missing endpoint at -1, -1. All right. Okay. So, by the way, we've shown that this is 1/2. DE is 1/2 of AC by showing our work there. Okay. Well, that brings us to the midsegment theorem. The midsegment connecting the midpoints of two sides of a triangle is parallel to the third side and is half as long as the third side. Now, note we did that over here, right? It's parallel. We showed that DE was parallel to AC. We've also shown that DE is 1/2 of AC. Okay, and that really is just showing the midsegment theorem. Okay. So this would mean that if we have DE and F are midpoints, so that would mean DE, DF, and EF, these lines right here making that triangle, are midsegments. We also then know, based on the midsegment theorem, that DF is parallel to the side opposite. So DF is parallel to BC. We also know that DE is parallel to, well, DE to AC. And the parallel lines are getting kind of goofy looking. Fix those up a bit. Okay. And we know that EF is parallel to AB. We also know, if this is true, if it's parallel to BC, if DF is parallel to BC, we also know that DF, the mid-segment, will be equal to 1/2 of BC. And the same thing is true here. If DE is parallel to AC, we know that DE is 1/2 of AC as well. And if EF is parallel to AB, we know that EF is 1/2 of AB. Now remember, it's because they're parallel and they are mid-segments, right? It's because they're mid-segments, or they're parallel and they go through the midpoints of the opposite sides there. That is the Midsegment theorem. So we can use that to actually solve some problems and to write some proofs if we wanted to. But if D is the midpoint of AC, so give another picture here, and E is the midpoint of BC, first find the coordinates of D and E, so and show that DE is parallel to AB. Okay, well the first thing is to actually find the coordinates. And you look at it, first glance, you're, oh, no problem, but then you recognize you have a bunch of variables here, and note you have some like tick marks here, and they don't really mean much of anything. So that's not going to help us. So let's first maybe start by, oops. Well, so let's first start by finding the midpoints, okay? So the coordinates of the midpoints, E, well, it's going to be helpful to actually use our midpoint formula. So remember the midpoint formula is equal to, it's an XY value, it's where you take your X2 and add it to your X1 and cut it in half, or take the average of your X's and the average of your Y's. Okay, so when I'm looking at this, if I'm trying to find the midpoint of E, and I know that E is the midpoint of BC, so that's this line here, that would be X1, Y1, and X2, Y2. Okay, so when dealing with that, I have 6Q plus 4P divided by 2, and I have 0 plus 2R. Divided by 2, which is equal to, well, looking at this, I can factor out a 2 on the top, so that's 2 times 3Q plus 2P all over 2, and 2R over 2, which simplifies to be, well, the 2's cancel then, 3Q plus 2P, don't know why I wrote that up there, for my X value, and my Y values, those cancel, so I'm left with R. Not an N, but an R. Okay. Now some would go, well, can't you just divide the 6 by 2 and the 4 by 2? Yeah, you could. That's called factoring. Just did that there to show why it was working. So point E, right here, we are going to call the ordered pair 3Q plus 2P R. Okay, and to find point D, well, point D is a little easier because you have 0, 0 here. So you're just going halfway to 6Q. Halfway to 6Q, that's 3Q. And 0, there, you don't move vertically, so it's still at 0. So there we go. We've got our mid-segment, DE. Okay. So now if I'm trying to show that DE is parallel to AB, I have to find the slopes of each. Well, remember our slope formula. Go ahead and switch up colors. So slope, which we call M, is equal to y2 minus y1 over x2 minus x1. Okay. So Slopes, m of, let's say, DE. Let's find the slope of DE first. Okay. Slope of DE, we are going to take our y2. So we got D, E. So we got, let's relabel these here. Y2, oops, excuse me, x1, y1, and x2, y2. All right. So we've got our y2, which is r, minus our y1, which is 0, over our x2, which is 3q plus 2p. Now, since it's a whole quantity, I'm going to put it in parentheses there, and I'm subtracting 3q. All right. Whoops. So, simplifying that, on the top I get r minus 0, or r. On the bottom I have 3q plus 2p minus 3q. So 3q minus 3q is 0, so I'm just left with 2p, right? These 3q's, they cancel. Okay, so I get a slope of r over 2p. Okay, well, let's hope the slope of AB is the same. So, kind of go through that same process there with AB. Well, this one's a little easier because you're dealing with zeros, right? So if we think of this as like my x2, y2, because I already got x1, y1 labeled here. Kind of make it 3D. Okay, so 4p, or excuse me, 0 minus 4p, and 0 minus 2r. Now notice I'm just kind of going through the process here, but except for I put them in the wrong locations. 2r's on top because that's our y, and it's y over x. Okay, so don't make that mistake. I get negative divided by negative, which is positive, so I get 2r over 4p. Well, you can reduce 2/4 to 1/2, so that's 1r over 2p. Hey, same slope. Of r over 2p. So, DE is parallel to AB. All right. Well, we also have to show DE is 1/2 of AB. Problem is, I'm running out of some room here. So, we're going to go ahead and separate this here. All right. See if I can fit it down here. So we've got to deal with distance now. Okay, so I'm going to find the distance of DE. All right, and remember the trick I showed you earlier here. Okay, so I've started writing out the distance formula here. I'm going to finish it up, but distance is equal to the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Okay, and remember we actually found those values right here. Here's y2 minus y1, here's x2 minus x1. So if we just square those values, we'll know the distance. So looking at DE, DE we have, well, x2 minus x1 was 2p quantity squared, and y2 minus y1 was r quantity squared. Okay, and so simplifying that, we end up with the square root of 4p squared plus r squared. Okay, and then the distance of AB. Now when we're doing that, you actually have to look at your original amounts before you reduce. Remember, this is your y2, your y1, your x2, and your x1. Oops, x1 there. Okay, so that's going to be our 2r over 4p. Okay, so the 4p quantity squared plus 2r quantity squared, and then simplifying that to end up being 16p squared plus 4r squared. Now looking at this, I can actually simplify. I could take a 4 out of each of those. Okay, so that gives me the root of 4 times 4p squared plus r squared. Okay, and then I can break those two things apart. So that's root 4 by root 4p squared plus r squared. Okay, well, root of 4 is 2. So that's 2 times root 4p squared plus r squared. So I have 2 of these roots. That's AB. And notice DE is one of those roots. So really, when I'm kind of summarizing this at the end here, you can say, well, I know that I'm trying to find that DE is 1/2 of AB. Okay? And I know that DE has a measure of 4p squared plus r squared with the square root of all that. And that's equal to the measure of AB. And the measure of AB is equal to 2 times the root of 4p squared plus r squared. So mathematically showing this, I'm going to fix up that there real quick. Mathematically showing that, note 1/2 of 2, once again, that's 1. And so these two things just kind of cancel. So I'm left with the root of 4p squared plus r squared is equal to the root of 4p squared plus r squared. So you've shown it mathematically by showing this equation equals itself. So as technically here would be your showing it. Okay, along with all your work there. Okay, all right, I think that's all I've got. Yep, good, lucky.